Hi everyone, today we will be going over the AP Calculus BC 2005 FRQ question 6. So first let's read the question. Let f be a function with derivatives of all orders and for which f of 2 equals 7. When n is odd, the nth derivative of f at x equals 2 is 0. When n is even and n is greater than or equal to 2, the nth derivative of f at x equals 2 is given by n minus 1 factorial over 3 to the nth power. Part A is asking us to write the sixth degree Taylor polynomial for f about x equals 2. That means we're going to be stopping when n equals 6 because that is going to give us a polynomial to the sixth power. Let's first look at what the general form of a Taylor series is. The general form is f of x equals sigma from 0 to infinity, f the nth power of f at a, x minus a to the nth power over n factorial. We need to keep in mind that when n is odd, the nth derivative of f at x equals 2 is 0. So the only n terms we need to worry about is n equals 0, n equals 2, n equals 4, and n equals 6. That means our sixth degree polynomial is going to look like 7 because the original function at 2 is 7 plus n equals 2, plugging that into our nth derivative function is going to give us 1 factorial over 3 to the second power times x minus 2 to the second power over 2 factorial, plus plugging the 4 into our nth derivative function is going to give us 3 factorial over 3 to the 4th power times x minus 2 to the 4th power over 4 factorial. And lastly, plugging in n equals 6 to our nth function is going to give us 5 factorial over 3 to the 6th power times x minus 2 to the 6th power over 6 factorial. And that is going to be our sixth degree Taylor polynomial. Part B is asking, in the Taylor series for f about x equals 2, what is the coefficient of x minus 2 to the 2nth power, for n being greater than or equal to 1? So something really important to look at here is that this is asking for the coefficient for when x minus 2 is to the 2nth power, not just to the n. So something helpful is that we already wrote out our sixth degree polynomial, and because when n was odd, we did not have any terms that had n equals 1 or 3 in them. So all of our x minus 2's are to the 2nth power, as you can see here. So this is asking for the general term of the coefficient. So looking at our previous polynomial, we're just going to be looking at this highlighted portion, the coefficient. And also, we're going to be starting at when n is greater than or equal to 1. So starting from here. Because finding a general term can be a little difficult, we're going to be breaking up the numerator and denominator of the coefficient. So first, let's look at the numerator. We see that it's 1 factorial, 3 factorial, 5 factorial. So it looks like our factorials are going up by 2. So we can say 2n. Plugging in the term 1, we're going to have 2n plus b, and we're going to plug in 1, which is going to give us 2 plus b, which has to equal to 1. That means our b is going to be negative 1. So the first term on our numerator is going to be 2n minus 1 factorial. Now we're going to be looking at the denominator. We can break up the denominator into two parts as well. the 3 to the n to the powers and the factorials. So first looking at the 3, we're going to have 3 to the second power, to the fourth power, and then to the sixth power. We can see again that this is going up by 2's, so we're going to have 3 to the 2nth power, and because plugging in 1 to the n, we're going to have 2, and that is what we're starting with. We're not going to add anything to it, which is just going to be 3 to the 2n power. And then multiplying, we're going to look at those factorials now. We have 2 factorial, 4 factorial, and 6 factorial. We see those are going up by 2's as well. So we're going to have 2n, and then once again checking for the b, we're going to plug in n being 1, which is going to give us 2 factorial, and that is what we're starting with right here, so we don't need to add any b term. So that's going to be 2n factorial. We know how to simplify these 2 factorials because this is basically 2n minus 1 factorial times 2n. That means this cancels out and gives us the general term of the coefficient as 3 to the 2nth power times 2n. Part C is asking to find the interval of convergence of the Taylor series for f about x equals 2. So first we're going to need to write the general term of that Taylor series. Since we know our coefficient for when x minus 2 is to the 2nth, we're going to say 7, because remember we're starting when n is greater than or equal to 1, plus sigma 1 to infinity of x minus 2 to the 2nth power over our coefficient we found right here, 3 to the 2n times 2n. Okay, so the best way to find the interval of convergence is to do a ratio test. So a ratio test, we're going to start off with the limit as n approaches infinity of the absolute value of an plus 1, which means x minus 2 to the 2n times x minus 2 to the second. Remember, when we add this plus 1 to the n, we're going to get 2n plus 2, which is equal to that, over 3 to the 2n times 3 to the second. Remember, it's not 3 to the first power. And then times 2n plus 2, because that n is multiplied by 2. Then we're going to divide by the original general form, which means reciprocal 3 to the 2nth times 2n over x minus 2 to the 2nth power. So we're going to cancel out these 3 to the second n power is going to cancel out, and we're left with limit as n approaches infinity of the absolute value of x minus 2 to the second power over 3 squared times 2n over 2n plus 2. Remember that this right here is going to be a coefficient, so we're only going to be finding the limit of this term right here. And remember, 2n over 2n, we can forget about this 2 because as n goes to infinity, it becomes not that important. So 2n over 2n limit is going to give us 1. So we have x minus 2 squared over 3 squared times 1 is going to be the answer of our limit. And when a ratio test converges, it has to be less than 1. So this has to be less than 1. So solving for the x, we're going to have x being between -1 and 5. Now that we found the internal interval of convergence, we have to check the endpoints. So checking the endpoint at x equals -1 and x equals 5, we're going to plug them back into our general series. So we're going to have 7 plus summation 1 to infinity of negative 3 to the 2n power over 3 to the 2n times 2n. So these two cancel out. That negative goes away because of the second power. And we're going to have 7 plus the summation of 1 over 2n. And remember that 1 half we can factor out and have 7 plus 1 half 1 over n. We know that from our rules that 1 over n is a harmonic series and that harmonic diverges. So that means at x equals negative 1, we're going to have a divergence by harmonic. Now we're going to check x equals 5. We're going to have 7 plus summation 1 to infinity. Again, 5 minus 2, 3 to the second n over 3 to the second n times 2n. These cancel out and give us the same series that we had before, 1 over 2n. And from our previous work, we know that this diverges by harmonic. So this diverges, and that means that we cannot include these endpoints, and our interval of convergence is going to be negative 1 to 5 with parentheses because those endpoints diverge. If you guys need more help with this topic, such as finding the radius or interval of convergence, I would recommend checking out 11.8 in the textbook and doing problems 3 through 28, and checking out 11.10 to find general forms of the Taylor series of a function. These are problems 13 through 20. And also finding the Taylor polynomials. 11.11, questions 1 and 2 are really good practices to find those Taylor polynomials.